Yeah. Maybe later work together. No, I get it. Yeah. That's page number 2. Okay, so let us finish up the ODE question and then we will do surface calculus. Okay, so last time we said that if the differential equation is non-homogeneous, okay, so the differential equation is not equal to 0, then we need to find the characteristic. Oh, sorry, not find the characteristic. Yeah, find the characteristic equation for the homogeneous part. Okay. So non-homogeneous part, you have two solutions, right? Okay. So it's the yt plus yc. Okay. So yc is the solution. The homogeneous counterpart. Okay, in this case is what? Y prime prime plus 4y equal to 0. Okay. So how to solve second order homogeneous ODE? Yeah, how to solve this equation here? You need to turn it into a characteristic equation. Okay, so what's the characteristic equation for this? Okay, so in this case here, you have two. How many roots do you have? R minus 2 and R. Wait, so what's this? Let me check. This example, where is it? So what root is this? This one, b squared minus 4ac is 0 minus 4ac, which is minus 16. Okay. So b squared minus 4ac less than 0. So this one is too complex. You know what are the complex root here? Okay, plus minus 2i. Oh, very good. Calculate faster than MIT. Okay, I equals to plus minus 2i. Okay, in this case here, okay, so this is a complex root. Okay, complex root. How to write the complex root? If I equals to a plus bi, what's the complex root? Y equals to a times c1 cos b. Sorry, eax, right? Cos bx plus c2 sine bx. Okay. Okay, so in this case here, we got c equals to c1 cos 2x plus c2 sine 2x. Okay. Okay, substitute. A is 0, so e to the 0 is 1. Okay, so but want to solve this particular equation here. So here got e to the x 3x. So what y you need to put so that you got e to the 3x? Huh? What thing differentiate twice you got e to the 3x? Huh? What? Huh? Same. Okay, you use same type of function, right? So you since the unsolution, so since the gx you have, or the non-homogeneous answer you have is 3 to the 3x. So you try e to the 3x, okay? But we don't know what coefficient to put. So we need to find the coefficient, okay? Right, e to the 3x is the one that you differentiate, you still get back e to the 3x, correct or not? Okay, so this is the possible, right? Okay, so you try and substitute this EYP into your differential equation and then solve it. So the differential equation is y prime prime, so 9a e to the 3x plus 4 times a e to the 3x equals to e to the 3x. Okay, so this means that you need to solve. If you compare the coefficient, okay, what you get is 13a equals to 1. So a equals to 1 over 13. So your particular solution is 1 over 13 e to the 3x. So altogether you have what? You have the particular solution plus the solution to the non-homogeneous. Plus 13 over. Okay. Okay. Hey, today you don't busy copying. Listen to what I say. Yeah. If makes sense, then okay. Okay, if don't make sense, then you ask. Okay, so the other type is sine x. Okay, so first, the two things you need to do, find the solution to the homogeneous part. Okay, first, and then solve the particular one. So if you want to solve the homogeneous part, what's the characteristic equation? R squared plus R minus 2 equals 0. So we need to solve the homogeneous part first. Okay. So this one implies what? R equals to minus 2 and 1. Okay. Okay. So your solution to the homogeneous part is just 2 real root. Okay, 2 real root. 2 real root is the simplest one. So you just use your root to build your linearly independent solution. Okay. Okay, so your gx here, hello, hey, hello. Your gx, hello, hello. So your gx here, right, is sine x. So what kind of y you want to try? What is the function that you differentiate once you will get sine? Differentiate twice you will get sine. Huh? Sine differentiate once you get cos, differentiate twice you get sine. Okay. Any other thing? Any other thing that differentiate to sine? No, man. Just now we passed by one function already. Sine differentiate once I get cos. Differentiate again I get sine. Cos, oh? Okay, only sine and cos can reach sine. Okay. So we need to take both because we don't know what to decide yet. Okay, so we take both. Okay, so we need to try both. So we set y as a cos x and b sine x. Okay, and then we differentiate and then plug into our differential equation. Okay, so we substitute all these value into our original differential equation. B sine x. Okay, so if you collect all the coefficient of sine x and cos x, you get minus a minus 3b times sine x plus minus 3a plus b cos x. Okay, you can quickly check. But on the right hand side, there's no cos, right? Okay, so you need to make the coefficient of cos to be 0. And then coefficient of sine is just 1. Okay. Okay, so in this case here, you get got something wrong. Anything wrong? Okay, so on one hand, you get b equals to 3a. Okay. Then on the other hand, you get a equals to minus 3b minus 3b minus 1. Okay, so you sub b as 3a. And then what do you get? You get minus 9a minus 1. Okay, then you get a equals to minus 1 over 10. Okay, b, in this case, b is minus 3 over 10. Okay, so all together, you need to put all the solution together. Size. So all the solution is the solution to the homogeneous part plus the non-homogeneous part. Okay, so non-homogeneous part is minus 10 minus 1 over 10 cos x minus 3 over 10 sine x. Okay, make sense? Okay or not? Yeah. Yeah. A sine, yeah, same. A and B is different. I put CD also can. Put kangaroo and zebra also can. Yeah. Seriously. They are just a holder. Also can. Also can. Hey, did I told you the story last time? Oh yeah, I said last time, right? This question. I said Hong Ming will ask this kind of question. If you put some minus now or what, it's okay because the minus absorbed by B. Yeah. Yeah. So okay. Okay, try this one. Okay. This one. So what's the solution to the homogeneous part? Okay, what's the characteristic equation you're looking at? Yeah. R squared plus 1 equals to 0. Okay, but this one, what solve this? This is a famous quadratic equation. This is the starting point of complex number. R squared plus 1. Okay, R squared plus 1 has no real root. Okay, why? Any number square is positive. Why positive plus a positive number you get a 0? Impossible, right? Okay, so we need to introduce this imaginary number. This number we imagine one. Okay, imaginary number. I. Okay, so this is the starting point of complex number. So I equals to plus minus I. So this is a complex, right? So we need to use the e to the ax cos x cos bx sin bx. So we get c1 cos x plus c2 sin x. Okay, so this c1, c2, right, is arbitrary constant. Remember last time, when can we determine c1 and c2? Only when the initial condition given. Okay, initial condition is given. So initial value problem is very important for your exam. Initial value problem. Okay, maybe you have to take note. Initial value problem, you need to take note. Okay. 所以要专心听啊。一般有保障哦。Okay. Okay. So yc equals c1 cos x, c2 sin x. So, but your function here is sin x, right? Okay, it's sin x. So your gx is sin x. So what kind of y you need to put? Huh? What kind of y you need to consider? You also need a cos x and sin x. But remember that we already have yc as sin x cos x. Okay. If you solve sin x cos x again, this answer will be absorbed into yc, right? You get what I mean? So you need two linearly, remember, for second order, the theorem, second order differential equation, you need two linearly independent solution, then the two add up will be all your solution. Okay. So you need to find another linearly independent one. Which one? Huh? Sine 2x. Sine 2x is the linearly independent to x. Ex sine 2x, but there's no 2x on the other side, right? How do you compare? Sine 2x must go to 0. Right. So what's the remember for the real root, for the same root, how to introduce the another linearly independent solution? Huh? Multiply by x. And then we also can multiply cos x sin x with x. Okay. So we consider what? We consider or we try yp equals to ax cos x plus bx sin x. Okay. So we can straight away compute it. X minus a x sin x plus b sin x plus bx cos x 1b prime prime minus a sin x minus a sin x minus a x cos x. So you need to do all the computation. And e power of x. Or you multiply sin x with e to the power of x. So you get the same thing after. You get the same thing after you differentiate. Will you get sin x or not after you differentiate ex to the sin x? X and x differentiate sin x or I just want sin x. One sin. No. I mean your right hand side here is just sin x, right? So if you sub y as ex sin x, will you differentiate to sin x or not? Will you get the term sin x or not? How? Product rule, right? It did sin x. No. Wait. So are you asking substitute e to the power x sin x like this? Yeah. So you do product rule, right? Okay, product rule, you ex sin x plus ex cos x. So you never get sin x. What do you mean by both sin x? You need to compare to sin x, right? On the right hand side. Yeah. Okay. I mean, the other way, maybe you can ask, how about x squared? X squared cos x sin x. X squared. Okay. Maybe you can try x squared. Okay. But I think you cannot solve it. Maybe you need to try. My point is maybe you can try this. Ax squared cos x. Maybe a1 plus a2 x cos x plus b x squared cos x plus b x cos x. Maybe you can try this. Yeah. Done. Okay, maybe I don't put so many a b c d. A b c d. Okay. Maybe you can try this. I think a and c must disappear. I guess. Right. Okay. Okay. So let's continue. So you could try this. So continue. So if we continue, then we will get minus 2a sine x minus. So I just sub this value into my differential equation, okay? And then I compare left and right again. Okay, so if I sub to the left one, I'll get minus 2a sine x, ax cos x plus 2b cos x minus bx sine x plus ax cos x plus bx sine x. Okay, equal to sine x. And then you will see that if you there's some cancellation here, so cos x will cancel. And then what else? Bx sine x also cancel. Okay, so what you left with is just minus 2a equals to 1 and 2b equals to 0. So a is equals to minus half. Okay, so your b disappear. You don't need the sine part. So your particular solution is minus 1/2 sine x cos x. Okay, so in general, the solution is the particular solution plus the homogeneous solution. Okay. Yeah. Okay. So these are some common gx you can solve here. So we only look at this ex, so exponential type of solution, or sine x, okay, involving sine and cos, or polynomial. Okay, only these three types only we look at. Okay, so for the second order differential equation, right, the important question is the initial value question. Okay, non-homogeneous one. Okay, sorry, homogeneous one. Okay, homogeneous one. Okay, homogeneous initial value problem. Okay, so meaning this type. So the one last time we did one. Have we done? Yeah, we done this. So this type of question very important. Okay. Is homogeneous initial value problem. Okay, like this. Huh? No application question. No homogeneous, not. Yeah. But be careful. Also have a look. I don't know later got accident. I don't know. Okay, but homogeneous one very important. Homogeneous initial value. Yeah, homogeneous. So for homogeneous, you just need characteristic equation, and then the three cases, which cases? Okay, find the root, and then substitute your initial value, get your CI, C1, C2. Okay, if it is non-homogeneous, you need to solve the homogeneous part first, and then guess the solution, and then find the coefficient. Okay, yeah. Okay, ODE. Okay, no concept one. Huh? Okay. 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 Very important. We have to go back to vector calculus. Yeah, vector calculus very important. Hello. 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 Okay, let's go back to vector calculus. So where we stuck last time? Uh, let me think. See. Okay, I think we start from Stoke's theorem. Okay, let's start from Stoke's theorem. I will repeat the theorem and then we will do exercise. Okay, don't worry. We will do exercise. So let's start with Stoke's theorem. What's the condition again? Stoke's theorem is a generalization of Green's theorem. Okay, they have the similar condition. You need to have a closed loop. Okay, so you need to have a simple, closed, positive oriented, and piecewise smooth. Okay, piecewise smooth. Piecewise smooth, you can parameterize your curve. Okay, positive oriented, you want anti-clockwise direction. Simple closed, you don't want to have self-intersection. Okay. So if you have simple closed curve, right, then simple closed curve bound a region. Okay, remember one example of simple closed curve is circle. So circle bound this. Okay, bound this. Okay. So in Stoke's theorem, right? What's in Stoke's theorem? Huh? So we integrate over C of a vector field. Okay, dr is equals to the curl. Okay, it's the curl. Okay. Why we swap position and take minus? That's the curl operation. Okay, the cross product. So it's the curl of F dot with the surface. Okay, you see, on one hand side you have parameterized curve. On the other side we have parameterized surface. Okay, so how to? So on the right hand side, so on the left hand side, we know how to do. Okay, we can parameterize our curve using RT. Okay, then there's an extra factor dropping out, which is the tangent vector. Okay, but how about the other side? How about the surface side? What happened to the surface side? Okay, what's the definition? Okay, this is the definition. Yeah, I'm going to tell you what's the definition here. So let's call our region D. Okay, and then the bound C. Okay, so what's the surface? What's the surface integral for a vector field? Okay, of a vector field. So because this is the surface integral, right? Better we draw double integral here. Okay. Okay. So what do we do? Okay. This definition here is integrate over a surface of curve F. Okay. Last time we used dot product. Okay, between tangent vector and our vector field. Now the vector you want to dot with is the normal vector. Okay, the normal vector. Okay, normal vector of dx. Okay. Do you remember what this normal vector is? Normal vector to a plane. What's that plane? Tangent plane. Tangent plane on the surface. Okay, how to find tangent plane of a surface? So you need the two directional derivative. Okay, you need the two directional derivative. Last time we call it u and v. Okay, so it's differentiate your surface with u, differentiate your surface with v, and then cross product. Divide by what? You need a unit tangent vector. Okay, divide by the length, and then dx. Yes, surface. Okay, but don't confuse the r and the r here. So the r on the right hand side is parameterizing a surface. Okay, so in other words, this RV here has two variables. Okay, the R on the right hand side, left hand side only have one variable. Okay, can or not? This two R is different. Okay, so last time we are stuck here. Okay, last time we stuck here. Or not we, me. I stuck here. Okay, so I have an extra length here. So what to do? Actually, we forgot. Okay, we forgot. What do we forgot? So actually, I forgot. So to do the surface integral, right? Okay. Last time we said that our surface is curved, but we cannot do integral on curved surface. So we need to make it flat. Okay, to make it flat, we need to introduce the Jacobian. Okay, what's the Jacobian? What's the area of a parallelogram? What's the area? In a cross product term, the length of the cross the tangent vectors. Okay, so actually there's a factor of the length of a tangent vector here. So if we change our domain, okay, back to the flat stuff, so we will need to introduce the length of the cross product or the area of the parallelogram. And then we write dA. Okay, so see, there's a difference here. Okay, there's a subtlety here. Here is dx, here is dA. Can you recognize this? Okay, so what does ds mean? ds mean they are differentiating on the curved area, but you can't really do it. So you need to put it back to the flat stuff. So which is dA. Okay, you understand or not? We will see example, but you get this idea first, then later we'll see example. Okay, get the idea first, then later I'll show you how to go from ds to dA. Okay, so if you go to flat surface, we introduce a Jacobian. So you see that length cancel with the bottom length. So in the end, what you need is just the cross product. Okay, so in the end, what you need is the cross product. Okay. If you understand what I say but don't believe me, it's okay. So you get my word first, later I'll show you. Okay, so this is the dot product, dA. Okay. So the moral of the story here is on the left, on the line integral, you dot your vector field with your tangent vector. Okay, but on the right hand side, you dot your curl F, also a vector field, with your normal vector to the tangent plane. Okay, this is the moral of the story. One, you dot with tangent vector of the line. The other, you dot with the normal vector to your tangent plane. Okay, this is the moral.
I can always change to a flat surface, so I don't have to do so much.
You can always straight away jump to the last one. You can jump to the last one.
You change variable, right?
Yeah, I have to change. Yeah. It's the UV. Yeah. The UV. Yeah. Okay. Okay. So if you see your lecture notes, right? Your notes, the dx, dA, dx, dA. So dx means the curve one, curve surface. dA, we already make the parallelogram flat. Okay. I'll show you example. Okay, I'll show you example. Okay, let's do example of this Stoke theorem here. So I think last time we stuck here. Okay. Okay, last time we stuck with this example here. So let us read this example again. So verify Stoke's theorem of the following vector field. Okay. If x is a paraboloid, z equals to x squared plus y squared, with the circle x squared plus y squared equals to 1 and z equals to 1 as its boundary. Okay. So do you know how to draw this surface or not? Z equals to x squared plus y squared. Which one? Stoke's theorem. 53 is one. This one. 53 also. Later we can go back. Let's do this one first. Because this one they already arranged nicely. So let's do this one first. So 53. Later we go back to 53 also. So verify this, okay? Do you know how to draw this surface or not? Z equal to x squared plus y squared. So when you see z equals to x squared plus y squared, right? X squared plus y squared is always positive. Okay, there's only positive z. Okay, and then this z change with the length of the function. Okay, length of the function. All right. So the diagram is drawn on the right hand side here. Okay. Can understand this diagram or not? Huh? Sorry? A ball, yeah, a ball, yeah. A ball. Okay. A ball. Okay. Actually, there's one more things I need to tell you here about this orientation. So we know that C is a anti-clockwise orientation. Okay, how about the region it bounds? Last time we said that surface is orientable. There's two ways you need to pick, right? Which side you need to pick. Okay, so which side you need to pick? Huh? What? Which side do you need to pick for surface? What is F? Left. Left. Okay. Huh? So I mean, your okay. So your orientation of your curve, right, need to align with your end. Huh? Yeah. In other words, is what? Is outward. Okay. Positive orientation. Okay. Outward. Okay. So okay. Later we will come back again. Okay. So let's look at this first. So okay, where do we start here? Okay, so we want to verify Stoke's theorem here. Okay, so this is a surface. Okay, this is a surface. We want to integrate. Okay, so in Stoke's theorem, what do we have? So we have line integral. Okay, the loop integral. Wait, the loop integral of f of dr, and then the surface integral of curve of f dx. Okay, so this is a two thing we need to compute. Okay. So what's the boundary of this surface? Okay, x squared plus y squared equals to 1. This is the boundary, right? Okay, so this is the boundary. So the C is parametrizing the boundary of my region. Okay. And then actually last time we computed this. Okay, last time I computed this. This is just minus 2 pi. Okay. But we haven't finished compute what's the surface integral of curl F. Okay. So let's compute this. Okay, let's compute this. So let's get rid of this thing here. So let's get rid of this. So get rid of this. Okay. So how to parameterize this surface? How to parameterize the surface? What's the x component? Cos theta. Cos theta. Cos theta. I think it's a bit harder if you want to use polar. You want to use spherical coordinate, is it? You want to use spherical coordinate, you say cos theta. Right. So let's restart the calculation of this surface integral. Yeah, let's restart this. Okay, so how to parameterize the surface x? Surface x is already given by z equals to fx. Okay, z equals to fx. So z equals to fx has a very easy parameterization. Okay, this kind of function, what you do is you just take x, y, and z as your fx. Okay, so in other words, what you do is you consider r of xy. X, you just take x. Okay, y, you just take y. And then z, you take x squared plus y squared. Okay, this is the easiest. Yeah, no. Okay, but there's a condition on this function, right? Okay, there's a condition on this. So what kind of x and y you need to take? Huh? X squared plus y squared less than equals to 1. Okay. Okay. Or if you like, you can write this as a polar coordinate form, which is easier. Okay, for later integration purpose. So this is just points with radius between 0 and 1, and from 0 to 2 pi, the angle. Okay. So this is all the point you need to consider. Next, we need to start and do our integral. Okay, we need to do our integral. But before doing integral, we need to know what is curl F, right? What is curl F? Recall what is curl F? What is curl F? Curl F is the gradient operator cross product with the vector field. Okay, so in this case here, we have okay. So in this case here, we get a z 0 and minus 2. Okay, you can check, but this is the thing we calculate last time. Okay, curl F. All right, so yeah, so let's see what else we need. Okay, so we start with this integral here, f dx. Okay, so by definition, this is what? Okay, so just now we computed, this is just But okay, let's repeat. The definition of this one is curl of f dot the tangent vector. Okay. Sorry, normal vector. Let me put all the stuff up. dx. Okay. Okay, so be careful here. Be careful here. So here, x here, right, have direction, but s here, there's no direction. Okay. Direction meaning I got vector. Okay. No direction meaning I already pull out the direction. Okay. But this surface here is still curved. Okay, it's still curved. So what do I need to do? So I change to flat one. Okay. So let me write some more. Okay. So I need to change to flat one. Okay. So I need to change to flat one. So after changing to flat one, right? You see, R is the flat surface, but D is not a flat surface anymore. Okay, D is not a flat surface. So we change to the domain of the curved surface. Okay, so from S, okay, from the surface S, we change to D. Okay, it's the domain that define it's the flat domain that define your curved surface. Correct or not? Okay, so you see D is flat one, R is a curved one. Okay, this R is the S. Okay, this is the X. This is the S surface. So this is the flat domain. This is the curved surface, right? Okay. Okay. So because in this step here, this is a one-to-one transformation. Okay, it's the change of variable. So you need to introduce the Jacobian. Okay, the Jacobian is exactly the length of our normal vector. So here become dA. Okay, why dA here? Because we already changed to r and theta. Okay, let me show you. So here d curve f of dot with the normal vector and then dA. Okay, so what is dA here? dA here is dr d theta. Okay, r is going from 0 to 1, 0 to 2 pi. Okay, curve f is z 0 and minus 2. What is n? What is n? Normal vector to the tangent plane. Okay, so what's how to find the normal vector? R, oh, so many R. R differentiate by R, okay, times R differentiate by theta. Okay, so in this case here, what is our tangent vector? What's our directional derivative? Partial derivative, sorry. So partial derivative is let me see okay. What should we do? Maybe we don't go to r theta first because our function is in xy. Okay, we do xy first, later move to r theta. Okay, let's do xy first, and then we substitute r theta later. Okay, so if we do xy, is 1, 0, 2x, correct? And then ry is 0, 1, 2y. Correct or not? So my function is here, xy, x squared plus y squared. Yeah. Okay. So what's my tangent vector here? Minus 2x, minus 2y, and 1. Okay. So we can put it back here. Okay, we can put it back here. It's in z, x. My tangent vector is also in x, y, z. Okay, all together is what? So z in our case become what? Z become what? x squared plus y squared. Okay, so actually this function here need to replace by minus x squared plus y squared. Right or not? Uh-huh. Yeah, cannot. Yeah, cannot. Cannot. Yeah, correct. So later we need to move all the xy into r and theta. Oh, you get what I mean? Uh, 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 uh. Later we need to change variable. Correct or not? But yeah, one thing you can do is change everything to r theta first and then do the dot product. Or do the dot product first and then change everything to r theta. Okay. Yeah. Because I scared, right? Why I don't want to change first? Because I scared very messy. You know, very messy. You see, if you change x to r sine theta and then y to r cos theta, there's a lot of things you need to write. Right. Let's compute everything in xy first, and then we change to r sine theta, r cos theta. Does it make sense? Okay. Make sense? Doesn't make sense. Either you change everything to polar coordinate and then you do the dot product, or you do the dot product first, then you change to polar coordinate. Same one, same one. Same. Same, right? Same. Should be the same. Yeah. Because changing the polar coordinate is in a professional term is invertible. So you can change back and change forward. Okay. Yeah. But yeah. Okay. So if you multiply first, what do you get? You get this. Okay. If you are not happy with this, right? If you are not happy with this, you don't want to do, you don't do this first, no? So you don't change to, you don't decide your variable first. Okay. So what you do is you just write in this form. Okay. If you don't, you are not happy with this. So you can write in this form first. Don't decide your variable first. You can do like this. Don't decide your variable first. Okay. But you need to know what you are writing there. That's fine. Okay. If you confuse yourself, hey, there's no r here, there's no theta here, how it cannot integrate, right? Okay. So make sure you don't confuse yourself. Okay. If you know, then that means we compute everything in xy first, and then we turn everything to polar and then compute. Okay. 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 So so if you don't want to see this confusing stuff, then we just put it at the side. Okay, so for now, okay, from now we can decide what is our dA. So our dA is dr d theta. Dr d theta. So we can sub already, right? So what we can sub? So x is r cos theta. X squared plus y squared is just r. Okay. And then what else? And then minus 2. Minus 2. Sorry, yeah, this one is r squared, correct? R squared. And then minus 2. Minus 2. Okay. Yeah, okay. So we go from dA to dr d theta, right? Huh? Go Jacobian again. Go Jacobian again. Right, go Jacobian again. Okay. So we got Jacobian again. So we got r here. Yeah, yeah, yeah. Okay. Mm. Okay. Go Jacobian again. Confused or not? So far, okay. Yeah, combine everything what we have learned. Yeah. Okay. But I mean, you need to really do it so that you will get used to it. Okay. Otherwise, you just know you don't know how to do. Okay. You have to practice. Practice. Okay. Mm. Okay. To the power 4 dr d theta minus integrate this or not. Okay. Yeah.
Once I change from DA to DR dividend, still have to add already.
That one is from double integral chapter. Yeah, right. Right. We didn't add to some. Yeah. Correct. Yeah. 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 So yeah. Yeah. So from DA to dr d theta, why we need to change is because from the rectangular to polar, we change again. We have Jacobian. So there's few Jacobian popping up here. One is from curved surface to a flat surface, okay, on xy. And then from xy to polar, introduce again Jacobian. So dx to dA got a Jacobian. After change to xy coordinate go to polar coordinate, Jacobian again. Right? This is the multiple integral chapter. Spherical coordinate got Jacobian, cylindrical coordinate got Jacobian, polar coordinate got Jacobian. Right? Okay, so yeah. First one make it flat, second one change variable. Yeah, correct. Last time we introduced one. From rectangular coordinate go to spherical coordinate, cylindrical coordinate, or polar coordinate if lower dimension. We also have Jacobian, right? Yeah, because those are because one is curved in 3D, one is curved in 2D. Make sense or not? 1D, just make it flat only. Still a 2D stuff. We just make it flat. And then we make it further flat. One is a flat in 2D, a 3D, okay, and then flat in a rectangular manner. Can or not? So the picture, okay, the picture in your mind, so the picture in your mind is, okay, maybe it is like this, okay, and then you make it, like this, you make it like this. Okay. No. This is concept. This is concept. Okay. You get a concept and then you still need to do the calculation. Okay. The calculation is just follow what I do. Okay. Okay. So how to integrate this? Okay. How to integrate this? Which one? Fubini's theorem. So first one I think is just 0, right? Okay, because you integrate cos theta from 0 to 2 pi. How about second one? So you get dr d theta, okay, which is just 1 and then 2 pi. Okay, so negative 2 pi. Okay, so we get the same answer with the loop. Okay, loop.
What's the original answer on the second one?
What do you mean?
The original is working. 我有用 area 那你比较有我这个就你的版本。You know, we introduce this one.
You mean I posted that one? Huh? I read up. I posted one. Huh? Okay, I'm sure you. Is this what you are referring to? This one. Yeah. This one. This one. This method. I mean, this is an example from book. I think, if I'm not wrong. You mean this method? Huh? Yeah. You see this method here. I keep it as an area. I don't go into variables. Okay. This one is using the double integral property. If I integrate the domain with a function 1, what I get is just the area of my domain. But this domain is what? This domain is a disk. So area of a disk is what? Pi r squared.
But you can't do part already.
I can't do two part. So I mean, wait. So you are talking about this one two part, this two part. So this one is just splitting out the integral. You're integrating two functions, right? So I just split out the integral. So for the first part, I go deep into the variable and then do the integral. Second one, I don't go deep because I know the property that integrate over an area with function 1 because I can pull out the scalar. So I'm integrating 1 on the domain. Then I'll get the integral will give you the area of the domain. So I don't need to do double integral. So I just compute what's the area of the domain. This is a quick way, but you need to know the property. Then you need to know the property and the concept well. If not, then you just do the variable. Okay, if you do the variable just now, what do we compute? We compute r squared, right? So this is the r squared that appear in the pi r squared. Okay. Yeah. Okay, now. Yeah. So it's like this one. So whatever you do, you will get the same answer. But if you can accept more concept, accept more properties, then you can do things easier, faster. Okay, no? Yeah. Okay. And yeah. Okay. So I mean, why people say max is hard, max is hard? Because there are different conditions allow us to do different things. Okay, so you need to consider a few conditions. Okay, because some people don't like to care so much. They don't care so much, so they are not sensitive. So they are not sensitive to the condition given. So yeah. So sometimes it's just hard to get it, but in the end you should be able to get it. In the end, okay. So my lecturer once said, my lecturer or my supervisor said, actually mathematics is not hard. Okay, just that sometimes you are not mature enough to accept it. Yeah. Once you mature, right? Next time I tell you this thing, you will say, very obvious one, no. But last time you don't know one. You know? Okay. For example, I also study first year maths. I don't understand. And suddenly, in the third year, I work on the rod. I understand why I learned. Yeah. So it takes time, really. It takes time. Okay. I mean, which rock? Next time I'll tell you. Okay. Okay. So yeah. So I mean, yeah, just sometimes you are not ready to accept it, but it's okay. But if you struggle, right? Next time you will be stronger. Yeah, next time you'll be stronger. Okay, any question between the two different calculations? No, okay. Okay. Okay, next one we want to do divergence first. Let's do divergence first. Huh? Okay, break open zone. You guys want to have a break? Break, Okay, 5 minutes.
天啊！
这条抓个啊！没有了。哎，那你好像很感觉举掉。可以的，可以的，要一下。
你现在是还没做
啊？什么？现在录了。没说啊，我没说啊。那个我来了，开玩笑啦。对，这个就这个，是吧？这个吗？要你孩子，这个梗，
我明天我要。你是这个，你要再到哪里？那你的来歪哦。
啊，对，比赛，跟我从习惯从最顶点，就是我比较理解，就是说，因为我现在有时候我是还是
对，你要先把这个来先看。
这个人很明显啊，就是应该是2码2.2啊，然后你叫比赛用比赛文玩的啊，然后讲比赛这个不能哦，其实不能，你要看那是ZY的，你要看ZY的话。
我们是领完，你们语气有没有这样？对，不是男女他在玩这个去吗？对，然后比较常见的那种情侣型的，
比如说 X 等于是多，它
没有啊，你要看这个切片，或者他是老你不懂 ？OK， 第一个你要看 ZY 边边，看 ZY 了，跟这个表情靠近表情。因为你定了你的 Z 是从减2到2嘛。可能你要看你的 Y 等于的，你的 Y 应该是等这样，你的个条件是 Y 等于等于 X 等于Y 等于等于，对 ，Z 是从哪里到哪里？最好会相信。对呀，它高的比多来，加减算法了。所以你要看 Y， 我现在是看 Y， 我的意思说 Y。对 ，Y 的话，Y 的话，下面这一个是，外面这一个是减 square root z，Y 等于减 square root z，上面这个是，哎，这不 Y 他要 fix 他的 z 线，可能你要 fix 他的 y， 对，因为你的 y 还没，我知了，其实这个是 y 减 z square， 要，这个是上个礼拜做的，我是下到这个不是，第上个礼拜他这边因为 z 啊，你刚才你 z 加减啊，你 square 的话一个哎，对了，我没有错，对，这个对，你要讲给这个人，round 比多百去调掉什么？我有画错吗？我应该没画错啊。因为我 y x 等于0的时候 y 所以这一条是讲你出来这条是哪？就做那个 这 square， 好，这样比较更容易，就选 dy dx 对，他要选，不要你，外面有来他。真的，因为我不会看那个懂咩，所以我要哪一个 example 随便拿，因为你看你2个 equation 这个要放进去一定对的。真的，我没有感觉这个方法真的对吧？这个，如果你现在你有点忘了，对。 我当时没有，我不理那个等下，我要懂，要去找那个左边先 dx dy 你再给，不要理他拿不学和是这个 negative 不是什么东西在这边，
你要做 dx 的，
你也给我讲出来。
我要做我想一下那个，
你要做 dx dy 的，
因为我其实我
要做 dx dy
啊 dx dy 的，那你就
老一种
对，就除了好是不是对，就是从右边常数这种，对，说不会考试，对，对，然后你那个
等一下我再重复，等一下我再重复，考试我再重复。
就是我问一下，你会是不是周一补的那节课里面讲掉了？
没有，还没有放回去，我等一下会讲。OK，等一下 ，OK，好了，OK，OK 啊。Okay, let's continue with divergence. Okay, 等一下我们再讨论。Okay, so next is a divergence theorem. Okay, continue. If we don't have time, maybe we will skip the 53. Okay, so next is the divergence theorem. Okay, these two theorem very important, but the exam type of question is a very simple one. It's simple one. These two will appear, but very simple question. Okay, the simple question means the domain lecture notes one, similar to lecture notes. Yeah, lecture notes one. And then how simple is it? So what you need to know is you need to know how to go from loop integral to surface integral. Okay, for Stoke's theorem. For divergence theorem, you need to know how to go from surface integral to volume integral. Okay, so meaning how to use curve, how to use diff. Okay, and the domain should be easy to integrate. Okay, the domain should be easy. What do you mean? I give drawn for you. It is not drawn, but it is very hard to very easy to see. Okay, very easy one. Just a simple one. No weird domain. Like sphere, like something like that. Very like circle, very obvious one.
Something like drawing.
Very obvious one. No like cut here, cut there. No like that. Yeah. I forgot what's the review question, but I think that one will be helpful one. That one will be helpful. Just simple one will be helpful. Okay. So divergence theorem. So let me start with divergence theorem. So first theorem we start with closed loop. Okay, closed loop. So divergence theorem we start with closed surface. Okay, everything upgrade to surface. So it's also a closed surface. So let's call it a closed surface. Say X. Okay, say X is a closed surface. So in line integral we have positive orientation, right? Surface, how to take positive orientation? Okay, the positive orientation we consider here is the outward. Okay, positive orientation. We consider it as an outward orientation. So outward orientation makes sense or not? So close loop, easiest example is circle. Okay. Closed surface, easiest example is sphere. Okay, it's sphere. Okay, it's sphere. So the positive orientation means all the orientation will go outside. Okay, go outside. Okay, go outside. This is positive. Okay. So from how to determine whether it's positive or negative? if you can write your surface as z equals to fxy, okay, your normal vector has positive k component. Okay, you make sure your last component is positive if your function is z equals to fx. Okay. Okay. So what's the statement here? So you have a closed surface, and then what you bound is your solid E. Okay, what you bound is your solid E. Okay, so bounding a solid E. Okay. So what's the statement here? So we need to relate surface integral to the divergence of f. So here is the boundary x, okay, which is the boundary of E. Okay, this is the thing you want to look at. This values here tells you how diverged is your vector field. Yeah, I will show you example. Okay, I will show you example. So let's see example. So there's another name for this divergence theorem, which is the Gauss theorem. Okay. So how you think of this is, you see, like you need to compare Stoke's theorem and divergence theorem. Okay, you need to compare these two. So Stoke theorem, you relate loop to surface. Okay, loop upgrade to a surface, closed surface. So you relate closed surface to a solid. Okay, but in Stoke theorem, you have curve. So in divergence, you have diff. Okay, you need to compare these two. Okay, they are parallel stuff. Okay, you need to compare these two. You get what I mean? So if I bring the Stoke theorem in, so Stoke theorem is something like this. Okay, so I put x here, and then here is curve f. Okay, okay. So you see, you upgrade your line to a closed surface, closed line to closed surface, and then upgrade your surface to a solid. But the function you integrate over is different. In Stoke's theorem, you integrate curve of f. In the divergence theorem, you integrate diff. Okay? Yeah. Because if you want to move in a circular motion, that is how curve is your vector field. How much your vector field rotate. Okay, this is telling by curve. But f on surface, it is an outward orientation. Okay, your surface is an outward. So if you want to align with your vector field, meaning your vector field, how it diverges. Okay, so the thing you put inside is diff f. Okay, because of the positive orientation I put on the surface. Okay, it makes sense or not? Does it make sense? Doesn't make sense. Minkai said doesn't make sense. Okay, you see, and remember this surface integral here, what do we need to do? We need to take the vector field, dot with the normal vector. Correct or not? If you want to dot with a normal vector, you need to align with the normal vector, right? So how much it align with the normal vector? Is the divergence of my vector field. So my vector field have the same direction with my normal vector of my surface. But this normal vector here is like going up. So that means it's telling me vector field, how my vector field diverge going up. Make sense or not? Correct or not? Dot product. When does dot product has meaning? Any degree cosine. When it is exactly the same. 0 degree. 0 degree minus pi, 2 pi, right? Same direction as long as, yeah. Okay, yeah. So if you align with the outward direction, meaning your vector field is like going up. Okay, so we call this a divergence. Diverge from the point going up. It makes sense or not? Okay. We do example. Okay, let's do example. Okay, do example. So do example. So we do this Gauss theorem here. Okay. So we compute these two numbers. So we compute the vector field, how much it aligns to the surface. Okay, how much it aligns to the surface. Okay. Okay, I think this example is quite important, so we start from scratch. Which is 53, right? 53. Correct or not? This is 53. So let's compute this surface integral here. Yeah. So you see, you see. So how do we align parameterize the surface, right? So first we want to compute surface integral. So if you want to compute surface integral, you need to parameterize your surface. Okay. So how many surface here? 2. Okay, x1 as x2. x1 and x2. So x1 is what? Z equals to y minus x squared minus y squared. Okay. X is easy. So because this is a z equals to fx, so we can just parameterize it as x, y, and 1 minus x squared minus y squared. Okay. So what is our domain here? Okay. The domain of this surface is just this. Okay. The domain of the surface is just as this. Anything satisfy this this. Okay. How about S2? S2 is what? S2 here is what? Yeah, right. So this is this on the z equal to 0. Okay, this is the this on the z equal to 0. So how to put this? You can write this as okay. So you could write it similarly. So you could write xy, okay, xy, but there's no height. There's no height. Z equal to 0. There's no height here. So you get the same d. You get same d. But there's no height. Okay? There's no height. All right. So let's compute the surface integral here. Okay, so this surface integral is not arbitrary integral, it's a special integral. Okay, when you compute this flux here, you need to make sure your surface is outward. Okay, outward orientation. Right, you need to make sure your surface is outward orientation. So what do I mean by that? Let's do the computation and then you'll see what is going on. Okay, so how to compute this? Okay, so because this boundary is split off by s1, s2, so I can compute integral on x1 and integral on x2. Okay, let's do one of them first. Okay, let's do x1 first. Okay, let's do x1. So what is x1? Okay, so what do we need? We need my f dot with the normal vector, and then I do dx. Then I do dx. Let me think. Not dx anymore. Dx after cancellation, we only left with dA, right? We only okay. So if you want to put dx, right, I think we have something like this. Yes. Yeah, before dx is this. And then we move to dA. Okay. Okay, let me write down step by step so that you know what's going on. Then if you write in exam, you can skip step. Okay, you can skip step. So
first step is like this. Okay, you have a normal vector divided by length of ds. Okay, I throw away the direction already. And then to make the curve flat, okay, I introduce this Jacobian on dA. Okay, and then finally we only integrate f dot n. Okay, so in exam, right, you can skip these two. So I go through the concept again for you, so that we strengthen our memory. Okay, so in the end, what you need to remember, you see, this surface integral here is really similar to the line integral. Okay, instead of taking dot product with a tangent vector, you take with a normal vector of the tangent vector. Okay, this is the punchline. Okay, you dot with normal vector of the tangent vector. So what is n? N here is Rx cross with Ry. Okay, what is our Rx and Ry in this case here? So our Rx is 1, 0, and minus 2x. I think we keep seeing this again and again and again. Okay, 1, 0, minus 2x, 0, 1, and minus 2y. Okay, for Ry. Okay. All right. So what is this cross product here? What is the cross product? If I'm not wrong, you will get 2x, 2y, and 1 dA. Okay, can see or not? Okay, you take the minor, and then take the minor, and then take the minor, 3 minor. Yeah. Okay. All right. So next is what? Okay, next you just do the dot product business. So you get 2xy plus 2xy minus x squared minus y squared. Yeah. Okay. Now you want to do double integral now. Okay. But this is dA in xy term. Okay. In xy term. But what's the easiest way to integrate this domain here? Polar. Okay, because we can describe this using polar. So if you go from rectangular coordinate to polar coordinate, you need to introduce Jacobian again. Okay, so we need to introduce Jacobian again. So all the thing inside here can be combined to 4r squared cos theta sine theta plus 1 minus r squared Jacobian r. Okay, dr d theta. Okay, and then you need to solve this. Wow, this is a bit a nightmare. Huh? Is not going to finish already. Today he is sleepy. Huh? Is it? Oh. Okay. So yeah, so compute this. So how to compute this? Okay, let's compute this. Let's compute this. Huh? Okay, compute this. Don't just copy. Check my calculation. Okay. Maybe I write one more step for you to see. Okay. And then I think a little bit easier now, so we can combine, make the double angle. Okay, from here, it's kind of straightforward already. All together, we will get I over 2 in the end. Okay, so the 1 over 4 cancel out. Yeah, this one just x1. Yeah, x1 is very hard. X1 is very hard. Because
the function, first of all, the vector field is hard. Second of all, is the surface. So when they put together, then they become a bit messy. And this is just x1. How about x2? Yeah, let's do x2. So, like what I said, in conclusion, what's the surface integral? Okay, the surface integral is just you take the integral of vector field dot with the normal vector and then dA. Okay, so this is the conclusion. Okay, is it similar to loop's integral, right? Okay, similar to loop's integral. Loop integral you dot with a tangent vector. Surface integral you dot with the normal vector. Okay, normal vector of the tangent plane. Okay. So what's the normal vector of this? What's the normal vector of the this? How do you know it's 0, 0, 1? How you calculate? You do a cross product. You do a cross product, okay? Actually, you don't need to do cross product, right? This thing is live on a plane. The what's this plane? Z equals 0 plane. Okay, what is the normal vector of Z equals 0 plane? 0, 0, 1. Okay, but you see, this is the key point here. We want the outward orientation for a closed curve. If I choose 0, 0, 1, right, pointing in or pointing out of the in, pointing into the solid or out? In. Okay, so we want out. So meaning we need to pick 0, 0, -1. Yeah, this is the point here. We want a durian. Okay, we want a durian. Okay, we don't want the things that go into. We want an outward orientation. So this is the key of the divergence theorem. We want outward orientation, positive orientation. Okay, you need to think of the surface as a durian. Okay, going out. Okay, can get it or not? Because 0, 0, 1, where's the direction? Going inside the solid. Going inside the surface. Make sense or not? So you want to go outside. Everything radially going up. Okay, so you need to pick 0, 0, -1. Does it make sense? Make sense? Okay, so we want 0, 0, -1. Okay, so in this case, we go to D of y x 0, y z and okay, y s z, but z in this case is 0. Okay, so it's 0. Stop with 0, 0, -1. Hey, note that our function is what? Our function is y, x, z. Okay, but why on x2 z is 0? Because my function lies on z equals 0. Make sense? Yeah. Okay. So we do this integral here. So what's this integral? This is just 0. This thing is 0. Because dot product is 0. Okay. So altogether, what do we get? We get have a 2. Okay. Okay, you can see that wow, this one so long. Okay. So exam will ask you to use divergence theorem. Let's see how does this simplify if we use divergence theorem. Okay. So let's do divergence theorem now. Does this simplify our work? Let's check. Okay, let's do divergence theorem. So let's check what is this diff f on E. Okay, diff f on E. Okay, what is diff f here? Diff f. Okay, diff f is defined by what? What is diff F? Gradient operator dot with my force. Okay, so I take my gradient operator dot with my force. Vector field. Okay, vector field is y, x, and z. Okay, so what do you get? You just get 1. Okay, good. Wow, this one very good. Huh? Integrate a solid over 1. What is this? This is actually a volume, right? Okay. So let's see, do we know the volume of this domain or not? What is this domain? How to describe the domain here? Let me bring the shape for you. How to describe the domain here? How to describe the domain? Let me copy paste this. Okay. Wow. Crop it. Okay, how to describe this domain here? Okay. So if you want to make it into polar, is it clearer or not? So the radius, okay, we make it into spherical, cylindrical. So the radius is 0 to 1. Okay. Angle is 0 to pi over 2 pi. Okay. And your z is still the same. Okay. 0 to 1 minus x squared minus y squared. But in the polar form, this is actually 1 minus r squared. Okay. So I don't think we quite know this formula, right? We don't know what's this, the volume of this shape. Right? This is not a sphere also. Okay, this is not quite a sphere. Okay. So we can just do it, do the triple integral. Yeah, just do a triple integral. So we turn our xyz into cylindrical coordinate. Okay. So let's turn this into cylindrical coordinate. So we do dz, dr, d theta. D pi, d0 to 1, 0 to 1 minus r squared. Okay, so go to cylindrical coordinate, you need Jacobian. What's the Jacobian? R. Okay, so you do this. Okay, so the hardest thing is you need to do 3 integral. Okay. I think this is easier than what we do just now. Okay. And then r cube dr. And then you just get 2 pi times r squared r over 2r 1 to 0 equals to 2 pi of 1 to 1 4, which is pi over 2. Okay. Yeah.
Like this area we use pi r square, right? Then this one can we use the cylindrical formula? The cylinder formula.
Don't get it. Calculate what? What do you want to calculate? Volume here. How you use pi r square to compute the volume? But this is not cylinder, right? The shape. This shape is not cylinder. This shape is not cylinder, right? This one. This solid is not cylinder. This is like the contact lens of. Not a regular solid that we. I think at least not in my mind now.
I get a cylinder, then I can.
If you use cylinder, you can get it. Yeah, you just use cylinder formula. Yeah. Yeah. Correct. Okay. The quiz, right? Actually, I just got it this morning, but no time to upload because need to split file. So I will upload later, so you'll see your result. I already posted out the solution actually, I think. You can check it in the Moodle. And then you can compare if anything's not wrong, anything wrong, then you can message me and then I will check. And then if it's okay, then I will add mark for you. Okay. So what time is it? 47. Oh what? Huh? Okay, tips are. Okay. Prepare a few things here. So in partial derivative, right? What have you learned? Okay. You learn level curve, level surface, and then you look at the limit of the surface continuity. Okay. Partial derivative, okay, fx, fy. And then you look at the tangent plane. Tangent plane, very important. Tangent plane. Later, I maybe take a photo. So, but you take note what is important first. Okay. So you have a level. Okay, in partial derivative, what have you learned? So you learn the function from R3 to R. Okay, so you draw a surface. You draw a surface, level curve, level surface, and then look at the limit, continuity. Okay, try to imagine what have you done. I go through the whole story. See you can put all the story together or not. Okay, and then we look at partial derivative. Look at x direction, y direction. How does the surface changes? And then we look at the tangent plane. This is where the partial derivative live. Okay, the tangent vector. So tangent plane is very important. Okay, how to find tangent vector. Okay. And then you can further differentiate. Okay, you look at higher order partial derivative. Okay, or the mixed partial derivative in particular. So how does this mixed partial derivative connected? They're connected by Claira's theorem. Okay, if the partial derivative is continuous, then they agree. Remember partial theorem. Fx y equals to fyx. And then we do chain rule. Okay, do chain rule on the full variable function. And then we do implicit function theorem. Okay. And then next, we not only can differentiate with respect to x and y, we can do for every direction u actually. Okay, which is called the directional derivative. Okay, how to find? What's the formula? The formula is the dot product of gradient and the direction you want to do the derivative. Okay, this one also very important, directional derivative. And then what's the maximum rate of change? Okay, it's the absolute value of my gradient. Okay, gradients tells you the direction you move the fastest, but doesn't give you the slope. You need to take the length. Okay, you take the magnitude. Gradient only tell you which direction is the fastest, but you take the magnitude, it tells you how fast is it. And then tangent planes to level surface, also very important. Maximum rate of change, very important. Directional derivative, very important. And then we go at local property. Okay, we look at the maximum, minimum values. Okay, we look at the maximum, minimum values. So they're split into absolute, local, and then there are extreme value theorem, critical value theorem. Okay, you need to have a look. So how to decide for critical points? Okay, what are critical points? Stationary points, and then boundary points, and then singular points. Okay, all these points, you see, either go up, go down, go up, go to a boundary, right? Okay, so every critical point is a turning point. Okay. Yeah, every critical point is a turning point. Okay. Yeah. So yeah, in Chinese is 危机就是转机。Okay. Yeah, but 听不懂华文 but English. Okay. Every crisis is your turning point. Okay. Every critical point is your turning point. Okay. So second derivative, how to decide whether it's local maximum, local minimum. Second derivative test, you need to learn how to use it. Okay, very important. Okay, next we go to multiple integral. So multiple integral, right? Actually, not much. Okay, just double integral, triple integral. Okay, but we keep changing domain. Okay, and also Fubini's theorem, we can change order of integration. Okay, and then the most important thing here is you need to know how to integrate over different coordinates. Okay, for example, from rectangular coordinate to polar coordinate, And in 3D, you need to go to cylindrical, go to spherical. Okay, this one I make summary already after chapter 15. And then the last most important thing for common exam is change of variables in multiple integral. Okay, yeah, you will be given a transformation. Okay, they will draw domain for you. You need to know how to compute the Jacobian. Okay, how to use the Jacobian. Okay, Jacobian itself can be positive and negative, but when we put into the integral, we need to add the absolute value. Yes, but in the integral, we only take the absolute of Jacobian. Okay, so that's why, so that we don't influence by the direction. No. Plus minus will give different integral. But yeah, Jacobian itself can have minus and negative, but when we put into the change of variables integral, we need to take the absolute value. Okay, otherwise it will influence the integral. Sorry? Uh-huh.
Is it wrong or right?
Wrong for what?
If they ask me to compute it.
Yeah, so it's wrong. Jacobian itself can be positive or negative. But when we always talk about Jacobian in the change of transformation integral, it has to be absolute. Okay. So I mean, okay, let me write down the equation for you. Hey, why like this? Hopefully no one's come. Maybe we will stay a bit longer. Okay, so let me repeat. Let me repeat. So this one is quite important and maybe easy to confuse. So if a transformation, okay, then if we change variable from rectangular coordinate to UV, okay, what do we have? We first substitute our xy in terms of UV first, okay, and then we introduce the Jacobian, okay, but the Jacobian here we put absolute value, okay, du dv. What's the Jacobian? Remember what's the Jacobian or not? The determinant of dx du dx dv and dy du. Okay, so if it is 3 by 3, then you need to include all the possible partial derivative. I think don't have too many things to do. Okay, okay. The last thing is not last yet. So vector calculus. Okay, vector calculus. What have you learned? So first you learn vector fields. Okay, R3 to R3 function from R3 to R3, and then you learn the gradient. Okay, gradient of a scalar field is actually a vector field. Okay, and then conservative vector field, when the vector field can be written as a scalar of some gradient of some scalar field. Okay, and then you do lines integral. Okay, you learn to do lines integral. Why you need to do in lines integral? You need to first parameterize your curve. Okay, parameterize your curve into t, and then there's a factor inside there, which is the tangent vector of your parameterized curve. Okay, you need to take the dot product. Okay, can remember? Can imagine what I said? Okay, nah? Can imagine or not? If not, I need to write down. Later, but now no time. So okay, so let me write down what I'm saying just now. So line integral, we have on the vector field. We have on the vector field. This is what is this name? Word done. Okay, word done. Physics name. So we substitute parameterized curve into my function. Okay, we dot with a tangent vector. Okay, dt. So t is going from sum a to b. Okay, so my curve is going from
A to B. Okay, so this is line integral. And then next we have a fundamental theorem for line integral. Okay, fundamental theorem of line integral. Okay, integral of C del FR dr. Okay, equals to. This is similar to fundamental theorem of calculus. Right, you take the endpoint evaluated at the endpoint and then minus the starting point. Okay. And then you have three equivalents between conservative vector field, okay, and then independent of half, line integral is independent of half, and then loop integral is always 0. Okay, if you integrate over conservative vector field. And then you come with this Green's theorem here. Okay, Green's theorem, just now we already repeat the higher version one, Stoke's theorem. It's the same as Green's theorem. Okay, you integrate around simple closed positive oriented piecewise smooth curve. Okay, this line integral is equal to the surface integral of the curve of the vector field. Okay, this is Green's theorem. So we have curve. After that, we have curve. Okay, and then if f is conservative, then the curve is 0. Okay, if the curve is not 0, and then the partial derivative is continuous, then f is conservative. Okay, if curve is 0, and then continuous partial derivative exists, then it is conservative. If curve is not 0, then f is not conservative. Okay. And then we have divergence. Okay, and then we have divergence, which is what is curve? Curve is gradient operator cross with vector field. Divergence is what? Gradient operator dot with vector field. Okay, there are two operations you need to remember. And then we have surface integral. Okay, so surface integral, you should really imagine the upgrade version of line integral. Okay, so you need to replace your line integral here with a surface. Okay, and then your line R become a surface R. Okay, so here R is in terms of T. So surface integral is what? Let me write down surface integral. So you need to integrate a surface, okay, on dRUV like this. Okay, sometimes we put X. Okay, sometimes we put X. Sometimes we just put EX. Okay, so these are actually lines integral of what I put here is a vector field. Okay, similarly, we have surface integral of vector field. These are the very important objects. Okay, very important objects. So what is this? So just now we already discussed that this is actually integrating over the domain D that define my curved surface X. Okay, so we imagine that our X is always curved in 3D. So flat domain D define curved surface X. And then what is it? So I need to take my vector field dot with the normal vector. Okay, normal vector. And then dA. Okay. What is the normal vector here? My X is defined using RUV. Okay. So what's the normal vector in this case? It's just RU cross RV. Okay, good. Okay. So how to compute the double integral here? You need to go back to the multiple integral chapter. You want to go from xy to polar, then you need to introduce the Jacobian. Go to different place, you need to, no different place, there's only one place you can go in R2. Just polar. Okay. Finally, any finally or not? So this surface integral here we call flux, right? Okay, if you see flux, then this is the surface integral. If you see work done, it is the line integral of vector field. Okay.
So you have Stoke's theorem. So Stoke's theorem very important and divergence very important. Okay, divergence theorem very important. Stoke's theorem very important. Okay. And then finally we have second order differential equation. So second order differential equation, there's not much thing we learn. So we only solve differential equation with constant coefficient. Okay. Once you have this, it can be related to the characteristic equation. Okay, then you solve for the root. So there are three possibilities here. Okay, so it is whether two real roots, two same root, or two complex root. Okay, then they have different solution to it. Okay. Nothing like that. Nothing like that. Must be different. No, must be different. Okay, no, that situation doesn't exist. Because b squared minus 4ac cannot both complex and both the same. Okay, so so for the main theorem in that chapter is this second order differential equation, right? If you already found two linearly independent solutions, you take the linear combination, those are all the solutions. Okay, so your key job is to find two linearly independent solutions. Okay, to the differential equation. Okay, so once you found the general solution have C1, C2, and the coefficient. So you need the initial condition, okay, to decide what is the coefficient you need to take. Okay, otherwise you just leave it as a general solution. Okay, so initial value problem very important in this chapter. Okay, so the part that I say is that I didn't say it's important, right? You still have to read because otherwise you won't understand what you're doing. Huh? I think about 5 to 6. 5 to 6. 5 to 6. Okay. I would say the computation should be easy, but you need to get the concept right. Then I think the result will just be quite easy to. Okay. Anything you want to do in quiz or not? You want to ask question on quiz? You got class? What time? Now maybe we take a photo first. How eh?
你觉得老师调皮的？最后一个看听。你们但是还有这些关系，那个中间他最后有很多人在这里，他只是问自己的，我们这里你的关系会他可以传在里面。你被看了。别人讲我们不要管，真的不要管，你要进场的，对啊，没有我没有钱啊，没有那个卡没有很多钱的，是。这个讲不错，我们拿过去打点我给他。
Hey, you guys have to move to these two rows. Move to these two rows. Front one can sit down maybe. Yeah. Oh, maybe like that. Oh yeah, like this. Maybe like this. Yeah.水龙，你要再进来一点，还是你去后面那一个坐？不能进，你不能。When Ken 是顶了。
好像要去中间，去中间。哎，你们过来，后面，你们全部过来，去中间。后面快点。哎，cover 了，前面 cover，全部要进来。关天，全部去中间，去中间。回去。OK。Yeah, okay. Yeah, like this, okay.
这个是啊，老师都这样，老师。
OK。不要。
什么红兵？你站在高后面，人不用看啊。
你搞我！看组长，老师在哪里？看哪一个是老师？就是的。
One two three.
1, 2, 3. OK， 追着。
哎 ，Thank you。啊，好了，走了，拜拜。
别做，在别的馆看到你啊。
啊？演讲？我的麦今天不能够用哦，2份。
别讲，老师，快来几句，来。
来几句。好。
我开电话。
Hello, testing。对啊，Hello。啊，Hello。晚上。MC 是你们要说。
他们那边。
So thank you for the semester. Your class is so far is the most proactive, most diligent, most animals, okay? Yeah, so I wish you all the best. You guys have the good character. You have the good character. So I think you will be very successful in the future. So if you try to have some plan changing the world, right? Please call me in. And if I'm gonna see you in the semester, then we will meet again. If not, I'll see you in the unit. Okay?
In the know?
You around the unit.
老师去叫 probability 啊。
Wait. So I really want to thank you because you guys.
不要怪我，你不要怪我。
So I really want to thank you because your class believe in me. So I will try my best to deliver my best. Okay? And then
这个不然你也不然你讲。
Okay, thank you. Wish you all the best. 所以去188他们讲啊，要不要去？
老师啊。
拜拜。
我要懂到你，你给我讲阿斌啊。
最后。
跟你们啊，我这边
不知道，我先打一下。
你们做打还是2阵还是你们也是龙的。因为我签一下，我签。我上次签到有一个，然后我没有看到。对，跟你们的规一模一样，就是你们的。OK 啦，等一下我再看多一次我刚才讲的东西给你们，然后你们再看一下。
我现在找那个。
LY9啊。
OK，下个。 我是
我也是两个都开始，
开始我们
我们聊这是不是？
没有啊。
啊，现在老师，
哎，你要还我钱，有没有还我钱？
你要付他点。
你要
还我钱，电话，搞我电话，搞电话。
你们要吃还是开心？
哎，他们今晚去118，你们要不要去？
可以炸鸡了，
是在那个
他们那个大圈子，
哪里？
那里面在旁边，对，就整只大，那边就没有啊。
是什么的？
吃钓菜吃也是钓菜吃，但是我们那种大酒那在机器按的是啊，不在机器按不好那个。那个直接在车前面有的。哦，对，没有。那你之前一天，哎，你
前一天来跟他要我的那才对的，
上面有报。他讲的。OK， 这样子，很简单。我们买了 KFC， 我们过去找你，反正都要让那个选队去找他了。
我多跟他们吃，
不然你打包过去 KFC 那边吃。
打包过去那边吃。
等下不给我订怎么办？
那我觉得可以。他这样控制你们的 KFC。没有，那也可以看到。那我上他们 KFC。
没有，
你们
014502310谁去？
我是想吃炸，我是想吃炸鸡啊。
大钱啊，9时点
你别我们
，9时点94、95、84全部都没买。
你要吃炸鸡，就是炸鸡啊。我要买这个，反正我们梗卖，来的这个是。这样过去的。什么？别点，不要点，解决。吃饭。
可以啊，
不能讲吃饱了3个，
主要就是
有人吃快餐，
是
快餐呗。先吃什么快餐？
会腻，我觉得会腻。现在
没事啊。忘记啊，你算一点，昨天吃我。
其实就是那些就是差不多的。
脆啊！重点你要的话，你们坐老师的车，我们坐
很头痛的东西。
因为我们讲
LY9吧。
走。
看他们要不要去啊？他们跟你的车。对啊。我们坐后面的车。
后面看我
去，他们有去买之前。后面开哈兰博基尼。你没有去吗？
没有去。
我5点半去啊。看你们。
可是我们在。
你不要讲话讲一半可以吗？
他5点半是你哦。
你们几点吃饭呢？那我们吃完去找你也是可以的。
打包先寄过去那边吃。哎，但是你们那边交菜。
我觉得不要。
可是你们没有开。
我觉得不要。我觉得不要。
哎呦，你2个都吃哦，你又不是吃不下。
你去那边有交菜吗？问题是。
我的钱包可以，
我的钱包
可以。
我现在
你们几点吃？你们几点去？
差不多啊，哦，先去收好几个啊！哦，可以，不要搞这样。
那你够，哎呀，一人1个不够啊，就14个。
我们这边啊，你们就整桌8个人，你们叫一个马来风光跟一个港工就好。叫人头帮我们带打鸡馆。
没有跟那个老板说。
啊。
都没去过。
不用紧啊，没有你就在那边洗碗咯。
这样上。
他不理你啊，自己紧张。
那你们几个人呢？
我们
哦，你可以生孩子，这样还可以做社长。
我没有啊，你讲出这个东西，我觉得是认真的啊。
明啊，
然后
OK，这是我们的鸡汤 OK。
哎呦，老师要飞啊，去送他。
你要是怎样啊？没有的，这个数学很简单的，你不会学罢了，你没有时间送他。
现在有这伙食了吗？
是，然后我会说开始。
没有，我学的，这飞伙食了吗？应该吧。没有撒拉瓦钱。我去别你对吗？我去别你，就是。
去别你就可以了，摆你就可以了，这个摆。
下个班入来，
师妹没有去那边吃一下什么东西？
一个礼拜啊，就是必须进，没有下面浪费钱，餐巾可以用。所以那做嘛就吃必须进吧，就是比较必须。那你每天吃这么多，给下面的话就值得了。就我随着中国国产，那你去中国吃必须进。
你是虎吧？我学到我学到
没有错，要多人啊，只要吃很花的。
越爽1比几？
我学了多了3.2
哦，也是不值得，哎。
老师看钱，看必须进多少钱？要不要算那边的号码？
对啊，那边嘛，
那也可以，你做那边钱花那边钱不一样吗？
你就相当于你在那边吃，这里也在这个，那边1个小时做10块。
就是1个小时换一盘必须进，还有剩。
是，
这一盘必须
美国工钱很高，你哪里外国工钱都很高。
我就老师也吃不饱
那很咸
啊，他的吃饱
它的
最饱
东西全部是秘密的。
啊，那就吃不饱哦，所以全部喝Coca-Cola，
一点区别
啊，全部当大字，
加全部没有，Coca-Cola 比白开水便宜。
他们吃都是，
对他们感觉
啊，是啤酒更便宜。
加油！
一杯吃饭的条件。
不是你至少有 record 到老师。